Good morning. This is Brian Faley from Outback Power, welcoming you to this webinar on a brief history of inverters, how Washington ruled the off-grid world. This is a bit of a look at how inverters kind of came to this area and some of our history. Also, a little bit of a personal history as well. And again, my name is Brian Faley. I'm the Senior Director of Advanced Engineering for Outback Power. This is kind of a picture, an overview of some inverter manufacturers that have Washington state roots. For some reason, it's been rather a hotbed of inverter activity since in the 70s, beginning with a company called Dynamo back in 1976. Another company called Heart Interface got its start, which spawned a company called Trace Engineering. A company called Xantrex purchased Trace in 2000. Outback Power was a spinoff from Trace, from some people who left to form Outback Power. Also another inverter manufacturer called Magnum Energy. But there's quite a number of companies that have been in this world. Rather small space. A lot of innovation also came out of it. This is just a kind of a brief overview of some of the products these companies produced. We've got Dynamo with a couple of products, an inverter called Brutus, which was the first sine wave inverter that's pictured there. Vanner, which had some mobile inverter products that was purchased Dynamo in the late 90s. And the Heart Interface started out with a mobile inverter, and Statpower as well was in the mobile inverter business. The Outback formed in the after the Xantrex merger, and Magnum after that. But the first products for both of those companies were actually mobile inverters, and then they moved into off-grid inverters. But again, all the inverters at the time were mobile inverters. So what is an inverter? An inverter is a device that converts direct current, PV or battery, to alternating current. Most modern inverters, which is post-50s, use semiconductor switches. In the very beginning, the challenging part of inverters was actually the technology. Power semiconductors, power MOSFETs weren't even invented yet. Power semiconductors were expensive and slow. We had a device called a silicon-controlled rectifier, which was like a rectifier that you could turn on. That was our switching device. It was rather hard to use, but we figured out a way to do it. It was very difficult to make sine waves, so most of the inverters at the time were square wave inverters. MOSFETs were just becoming available. They were very, very expensive and very delicate. And in terms of the processing power behind making the decisions and the logic that drove the inverters, it was all discrete logic, mostly CMOS, and there were no microprocessors at the time that were used in inverters. So this is circa in the early 80s. First Washington manufacturer of inverters for off-grid use was Dynamo. That was founded in 1976. Most of the inverters were square wave inverters. They built a line of battery-based inverters for off-grid and mobile use that ran power levels from 500 watts to 6 kilowatts. They all used SCRs, which was, like I said, a semiconductor switching device that turns on very easily, but turning them off is difficult. You have to use another device to turn them off. The efficiencies ran in the 80 to 94% range, with total harmonic distortion on the output about 45%, which is basically a square wave, which is pretty horrible. But at the time, there was no other alternative other than a mobile generator set. they were available in a wide range of battery voltages because those are the common voltages of the day: 12, 24, 36, and 120 volts DC. The idle power of these units, because of the way that the switches switched, and they took many microseconds to switch, consumed about 250 to 500 watts. All of the logic that was used to drive them was CMOS logic, which was discrete and wasn't very flexible, and they usually used ripple counters of some sort. There was no voltage regulation, so the output voltage was directly a response to the battery voltage. They were also quite heavy, in the order of 100 to 120 pounds for a 4 kilowatt inverter. One of the first inverter manufacturers to use MOSFETs was a company called Trace Engineering, and what they pioneered was they were the first UL listed inverter. They listed to a standard for a mobile inverter at the time, which was UL 458. And this is a picture of that product, the U-series inverter. It was a 2500 watt 12 volt inverter. It used what was called a push-pull setup, which alternates the conduction of the MOSFETs. And then during the time interval between when the MOSFETs are switched, there was a clamp winding that was used to hold the voltage on the output at 0. And so you ended up with a stepped approximation of a sine wave. The voltage regulation that was used, as I said, was called quasi-sine wave, and by adjusting the time that the transistor spent on, you could adjust the RMS output voltage, and regulating that allowed it to produce a sine wave with 120 volts and used for a lot of equipment that seemed to work just fine at the time. One of the innovations, another innovation of the Washington-based inverter companies was they were the first to actually use an H-bridge, which allows you to change the direction of the current just by deciding which device to turn on and turn off, which allowed, with 4 transistors, you could control the output and make a quasi-sine wave. There were a couple of other innovations in the field, which was the advent of planar MOSFETs helped to drive this. These devices were being used in the automotive industry, and the prices were coming down. Some of the brands of the time were Trace U-Series, Legend, and DR. Dynamo had an inverter called the Bravo. Vanner had an inverter called the TQ. They were all quasi-sine wave inverters that had RMS voltage regulation. It was quite innovative at the time. It allowed a much higher efficiency. But the downside of the MOSFET inverter with the quasi-sine wave was that the peak voltage varied with battery voltage. So as the battery voltage was higher, you reduce the amount of time that the inverter spent on at the expense of a higher peak voltage. And then as the battery voltage fell, and this graph kind of shows it, the brown line at the top is at 14.5 volts of battery, which is a battery that's undercharged, and the lowest voltage is pretty close to a square wave down at 10.5 volts. And a lot of these products on the original inverter world were frequently low voltage products in the 12 to 24 volt world. So the simple voltage regulation of the quasi-sine wave had problems in that the peak voltage varied pretty dramatically over the battery voltage range. It also wreaked havoc on things like sound systems. A lot of people in the remote world, in the off-grid world, like to run their stereos and television sets, and it was kind of problematic. It created hum, and the television sets, it created a roll in the horizontal. So it was not very friendly, but it was better than having no power at all. Sine waves first came on the scene in about 1984, which was pretty late in the history of the inverter, but it was a much more difficult thing to do than it had first appeared. Required some pretty significant advances in the technology, both in the MOSFETs and in the control schemes. In 1984 at RETC, which was the kind of like the Solar Power International of the time, Dynamo introduced the UXB series of 24-volt inverters, making sine waves. It was a high-frequency design. It was about 25 pounds and 3.6 kilowatts. It actually never made it to production. The following year, the competitor of Dynamo, Hart Interface, introduced the X series at the same show, and there was actually a lot of traffic between the two booths, with quite a stir over this availability of sine waves in a world where sine waves really didn't exist. In 1988, which is 4 years after the first introduction, the first commercially available inverter, sine wave inverter, the Brutus from Dynamo, was produced. Richard Perez of Home Power magazine was an early fan, saying that basically it would power anything he threw at it. But one of the reasons that limited the availability of the sine wave inverter at the time was it was simply much more expensive than a quasi-sine wave inverter, which was adequate for many people's needs, and really hadn't taken advantage of the MOSFET pricing was still very expensive, and the other penalty was a fairly large amount of idle power. And in the off-grid world, that was a big deal. In the early 90s, a company called Trace began producing a sine wave inverter called the SW. It used a different technique to create the sine wave based on steps rather than pulse width modulation, which the other companies used. It used a much lower switching frequency to do that. And it had a couple of big advantages. One was it had two AC inputs, so you could have a generator and a grid input. So you could charge your battery from grid, or you could charge your battery from a generator. It also only produced single phase AC, and it could be series stacked. So you could stack two inverters to get 12240. It had fairly low idle power of only 20 watts. So when in a world where solar panels were close to $10 a watt, consuming any excess energy was kind of forbidden, and the product was created with a very, very low tear loss to do that. Let's see here. There was a lot of innovation that was going on in the industry, and there was a lot of competition between the inverter manufacturers, and that spawned some intellectual property, some patent wars, and a lot of rush to protect inventions. They were also protected largely by trade secret. This is kind of a really brief schematic of a low frequency inverter, showing that the reason it's a fairly efficient inverter is that it has a single conversion. So directly from DC on the left, the MOSFET switches are switched in an alternating pattern that allows a direct conversion from AC to DC, or DC to AC, and that passes to the transformer through an output filter. It's easily scaled with the transformer. It's a 60 hertz transformer, easily scaled for output voltage, so 120 or 240 volts on the same winding. It's very easy to do. Also, because it's a bidirectional converter, if you switch things around and apply a grid to the input and synchronize it, you can create a power factor corrected battery charging, which was another innovation of Washington State inverters, were the very first inverters to use power factor correction in their AC battery charging to improve the amount of energy that could be delivered from a limited feed and improve the quality of the input current. You see a lot about the low frequency transformers versus high frequency transformers. This is just sort of a picture showing some scale. The one on the left is a 60 hertz, 4,000 watt transformer. It's about 35 pounds. And the one on the right is a 40 kilohertz high frequency transformer used in a high frequency inverter. And that just shows that as the frequency of the inverter switching goes up, the physical size can be brought down pretty significantly. The downside of it is that the output's not directly usable, so it has to be converted again. This is a schematic of a high frequency inverter, and as you can see, there's a lot more going on in here. There are more parts, it's much more complicated. It takes 2 stages and actually 3 conversions to go from DC on the left-hand side to AC on the right-hand side. Typically, the DC is converted from a low voltage battery voltage up to a higher voltage, something intermediate between 250 and 400. And then that is then converted again down into output. And they're often called high frequency inverters. But the middle section, the H bridge following with the output filter, is actually the basis of most grid-tied PV inverters that are used today in industry. Again, if you look at just the right-hand side, the H bridge with the output filter, that's the schematic of most grid-tied inverters, and they operate with an input voltage in the 250 to 600 volt range. But as you can see, it's a lot less complicated when you do a high voltage conversion with a transformerless inverter. With this high frequency inverter, the bidirectional power flow is possible, but it's actually difficult because of limitations. And again, because of the 3 conversions, the efficiency of this type of an inverter is lower than that of a low frequency inverter, because it's 3 power conversions, and each time the output, the overall efficiency is a product of each conversion. So even if you have 2 converters that have 90% efficiency, the overall output efficiency is only 81%. So to get 90+ percent efficiencies, you've got power stages that are in the hundreds, or they're nearly 100%, so in the 98% range. To get an output efficiency of 95% with 2 conversions, you'd have to have 2 converters with 98%, which means it's a more expensive inverter than it would be otherwise. There were some substantial challenges in the early days of inverter manufacturers in Washington State. There were some very strong personalities, which went from company to company. If they didn't like the way they were being treated, they moved on. There were some very big ideas, strong competition. It was a fairly limited market. There were 3 companies in Washington at one time operating at the same time, battling each other in the marketplace, but also suing each other back and forth over patent infringement and things. But there was a large amount of entrepreneurship and innovation, because in order to make something that was different, you had to do something better. So many of the original inventors came from audio or aerospace electronics background. A couple companies that come to mind are Phase Linear, Symmetric, and Eldec. Those are all aerospace and audio companies. But again, there's a lot of similarity between a high-powered audio amplifier and an inverter. On these pictures, this is sort of a history. This is a number of the manufacturers insisted on making everything here. The far left picture is a picture actually from Magnum Energy when we started up. I was an owner there. That company built all of the product here in Washington State. The middle picture is actually out behind Trace Engineering before just after the Xantrex merger. And the far right there was my lab at the last place I worked. Again, it's a lot of innovation happened on a bench top. Some of it happened in homes, and it was driven by the market need and a desire to give people products that they wanted. There was a lot of consolidation and some stifled innovation. Statpower was acquired by Xantrex. They were a power supply manufacturer in Canada. Statpower was an early high-frequency inverter manufacturer. Trace Engineering then merged with Xantrex, and then they bought Hart Interface and cruising equipment. Cruising equipment produced a product called the E-meter, which was used for battery state of charge monitoring. Xantrex then dealt with this thing that they'd purchased, which was this conglomeration of 3 different inverter businesses with very different understandings of the way to do things. There was an attrition from that. Outback was formed from former Trace employees. They went after the off-grid and grid-tied markets. Magnum Energy formed by former Trace employees. It went after mobile and off-grid markets. Schneider then bought Xantrex. Alpha Technologies bought Alpha, and Sensata fairly recently purchased Magnum. So there's been a lot of hands changing. These typical companies lasted in the order of 8 or 10 years before somebody decided that it was time to do something different. Some of the innovations in Washington inverters that came up with was battery-based with and without grid tie. Outback was an early manufacturer of grid-connected inverters that did grid ties, so they would both buy and sell power to the grid, as well as Outback built charge controllers that would charge the batteries so you could sell PV. Most of the products built in Washington were single conversion with a high efficiency. They were considered very robust. Outback pioneered sealed inverters. The FXR inverter came from that line. They're very rugged construction, they're reliable operation. The other thing was field replaceable components. Many of the smaller inverters would, if they broke, you'd ship someone a new one. But in an off-grid situation, the availability of replaceable components made it more easily serviced. Also, some products that are different were the highly integration system in a box, like Outback's new Skybox inverter, which got the charge controller, the inverter, and the battery interface all in one box, or the energy management system on top of that. Transformerless inverters with energy storage, another thing that's unique. Also, in terms of the assembly, because many of these products were assembled stateside rather than overseas, had to come up with ways to be able to produce them less expensively without having to deal with offshore manufacturing. So clip mounting of MOSFETs reduced assembly time. Wide use of service mount in power boards, use of the COVIA's technique for high power through very high current connections, replaceable power boards, field upgradable firmware, data logging faults, so fewer returns. Also, you could look inside systems in the field and monitor them and find out what's going on inside. Fully programmable parameters. That's been a big positive thing in the off-grid systems because there's so much flexibility. And then the other one is paralleling inverters for higher power. There's a lot of inverter manufacturers in the world who don't allow parallel systems. These products were all designed from the ground up to do that. And then again, UL 1741 compliance, and that's for the grid connected inverters, off-grid inverters with grid connections. Regulations were something that came into the industry. There were a lot of reasons for the regulations, but the regulatory requirements were becoming more and more stringent, and that's particularly as there are more inverters connected to utility grid. The larger the number of inverters, once you reach about a 10% connection capacity, you begin to impact the grid, and you have to be able to play nice. So there were some regulatory changes that came, UL 1741 SA, which is supplemental annex, which is the smart grid standards coming to the grid, DC arc fault changes. Those are currently in rework right now with, again, as a result of regulatory requirements coming into the industry. National Electrical Code dealing with a large number of PV inverter installations worried about firefighter safety and other things. And an increasingly challenging utility environment because high levels of PV penetration destabilize existing grids or can destabilize them. And the emerging grid standards, which come under the heading of 1547, which is a standard for distributed energy resources, basically outlines the ways to make interfacing energy storage inverters with the grid more beneficial to both. So, and the energy storage market's exploding because in many parts of the country, the cost of energy is becoming higher, particularly under peak demands. And there's many places where there's peak pricing, time of use metering coming into place. So the time when energy is being generated versus when the time that energy is being consumed don't always line up on a time scale. So the ability to put energy into a storage application, into a battery, and then use it sometime later, that's exploding. And the smart grid standards require smarter inverters. Many of these other inverters I described, these old inverters, were simply, they just made sine waves or just made power. They didn't have any sophisticated features other than the ability to disconnect from the grid when the grid frequency or voltage was out of range. But they couldn't supply things like reactive power factor. They couldn't do volt var. They couldn't do frequency watt, which are smart grid standards that allow large systems to work together without having to have direct communication. In addition to that is the SunSpec, which is a series of inverter manufacturers working together to work out a common framework for a communication system to talk to the smart grid. The idea that the smart grid is going to reach out and take control of your inverter and do what it wants with it, it's sort of big brotherish, but it is pretty common in large systems for that to happen. And being proactive about making sure we all agree on the terms of how things operate is a pretty large thing to work on. Some of the technology trends, the direction things are moving now is obviously DSP technology, the advent of low-cost microprocessors and high-powered digital signal processing is being used to more precisely control the power conversion. Gives you good phase angle control on frequency and reactive power. And it's lowering the cost of power inverter systems. There's been some new topologies that have come out which have much higher efficiency, neutral point clamped, H6, some transformerless, and there's some low frequency based ones as well. Pretty substantial advances in power semiconductor technology are on the horizon. They're just emerging now, and we're beginning to see them penetrate in some of the higher end applications, improving the overall system efficiency and lowering the cost. The adoption of wide bandgap semiconductors to increase efficiency is being seen in some of the higher powered inverters today. The advantage silicon carbide and gallium nitride are two high voltage switching technologies that offer literally an order of magnitude improvement in switching speed, which should increase the efficiency of these systems and bring the costs down. Also, higher power factor with integrated form factors are increasing system size. 5 years ago, the average size of a PV inverter in North America was around 4 kilowatts. Today, it's close to 7.5, and there's places where that's getting even larger. Energy storage as a part of the integrated system is becoming more and more common. Many of these battery-based inverters, and that's what I've mainly been talking about today, because the roots of the renewable energy world were off-grid because in many cases people didn't have another method of generating electricity. Battery systems provide not only backup power, but they also provide load management, because you can time shift the when you charge the battery versus when you use the power. And we're seeing a much larger prevalence of integrated energy storage, and you're seeing that today in the grid-tied world as well, with many of the grid-tied inverter manufacturers offering either parallel battery systems or batteries for self-consumption, which means you're using the energy that you generate, and by being able to putting it into a battery, you can use it when you need it rather than when it's available, which doesn't always line up with when your loads are. Also, real-time communications of performance data and inverter parameters is pretty crucial to the management of large inverter systems and for smart grid readiness. It's a pretty sophisticated scheme of communications, both internet, Ethernet connected, and some of the Modbus things with SunSpec. Allow inverters to, with the same set of commands, you can control any inverter, and that's a pretty important. And this is the time for questions. I think you have a click bar on your. I'm pulling them up right now. But if anybody has any questions now, it'd be a good time to ask. This is actually a picture of me from the early 2000s testing grid-tied inverters in Davis, California. I appreciate you coming. If you have any questions, just let me know. I'll be here for at least a few more minutes. Okay, I just got one about the, do you anticipate the physical size will get any smaller? We're already seeing the physical size of inverters getting smaller, particularly as some of these wide band gap semiconductors, we're seeing inverters getting smaller. The line frequency based inverters aren't going to get much smaller because the line frequency transformer pretty much dictates the size, but the sophistication of that inverter is getting much more sophisticated. So there are going to be and there are in process designs being worked on that are going to be offering smaller inverters, particularly as we move to the isolated higher frequency topologies. Someone asked who I work for now. I work for Outback Power, obviously, but I've worked for about 8 inverter companies over my career of 37 years. Okay, in terms of someone's asking a question about capacity. Most of the, well, I can talk now about the Outback product. Our flagship product is an 8 kilowatt inverter, and it stacks up to 10, so you can go as high as 80 kilowatts on a 48 volt system with our product. With our Skybox product, you can stack at least 4 to 6 of those, and those are 5 kilowatt fully integrated systems. In terms of stackable inverters for 3-phase systems, you can take our FXR inverter and stack it in 3-phase configurations. So that's something we do today. Does the Skybox compete with an AC coupled system? It can. The advantage of the Skybox is an all-in-one. It doesn't require another inverter to operate. So we're seeing applications where that's actually going in and replacing an AC coupled inverter with a PV inverter. Will an inverter lose some of its capacity? No, it shouldn't. At 10 years, the electrolytic capacitors, if the inverter has electrolytic capacitors inside, the electrolytic capacitors may not be as good as they were when they started. It depends on how heavily it was used and what temperature it was operated at. That's something that actually, in some products, can be upgraded, but the inverter doesn't really lose its capacity. It's wearing out is what it's doing. Higher capacity skybox in the near future. That's a really good question. That's being worked out with product management right now. Any other questions? If there are no other questions, then I'll thank you for your participation and appreciate you coming to the webinar. Keep your eyes open. There'll be more of these in the future. Thanks a lot. I just got a question about connection between audio electronics and power electronics. That's probably not a question I can answer here, other than the connection is that they both use semiconductors. They're both basically Class D amplifiers. So they share a lot of commonality in that high current, low voltage space.